Um, in this little introduction, I am not I will not discuss the um, I will not discuss the issue of the solution to a problem on exercise, but I wanted just to say something about the Riemann integral and the flaws associated with the Riemann integral and the need for mathematicians to come up with something more general integral. So the answer, of course, was given in 1902 by Lebesgue, French mathematician. And before I go into this, what are the difficulties that the people dealt with when dealing with the Riemann integral? Okay, so let's go back. We have to go back to the concept of Riemann integration. So how did we do it? So we take a function. Okay. So first, of course, we go for a positive function, and by taking the difference between the positive part and the negative part, then we can get the integral of any function. But let's just focus on that. So first of all, we take a function, take a and b, and this is just again to illustrate. I do not want to discuss the case where the domain is infinite and the function becomes infinite. In other words, the case of improper integrals. The point here is just what are the fundamental limitations of the Riemann integral. This is very interesting. So the approach that was given by Riemann was, and keep in mind that the Riemann approach was more of a geometry approach. It was about finding the area of uh, a region. Okay, so the concept of antiderivative as introduced by the Newton school, uh, it was bridged with this concept through the fundamental theorem of calculus. So in any case, I want to focus mainly on this. So this was motivated by the area problem, and that's why they were able to take what? To take these slices, okay, of the graph, and then uh, approximate them when the width here becomes small, to approximate them by rectangles and add them, which will give us the Riemann sums to find an approximation of the area, okay, which will become what's known as the Riemann integral. So the fundamental here approach was to look at the interval AB and slice it into, or what's known as a partition. So we partition this interval AB, and then from this partition we generate a simple function, either the lower sum or the upper sum. So if we call this one x0 and this one xn, x1, xi plus 1. So we generate these two numbers, okay, mi, which is the infimum of f of x for x between xi plus 1, as well as capital Mi, which is the supremum of f of x, where x is between xi plus 1. So again, I'm trying to discuss here the issue of Riemann integration and the flaws in the Riemann integration. So whether the function becomes infinite and we have these problems. No, let's just take a bounded domain, okay, for the function f, as well as the bounded range. Uh, so now using these two numbers, you come up with what we call the lower sum of f with respect to this partition here, which is sigma of mi time the length of the interval xi plus 1 minus xi, and you have the upper sum, which is sigma of capital Mi xi plus 1 minus xi. Okay? So, of course, what are the simple functions that will approximate my function. Okay, so we have these two functions. Okay, so we have these two functions. Let's call it small simple function s of x, which is sigma of mi, okay, xi plus 1, and capital S, which is sigma of capital Mi, the characteristic function of the interval. Okay, so these are the simple functions. That's basically, so we know that s of x will be less than f, will be less than capital S. So you see, when we have a nice function, we'll say that f is Riemann integrable if you are able to find this kind of simple functions below and above, such that their sums or their integrals will be close to each other. Okay? So the problem here is what? That these simple functions are all obtained from intervals. Okay? So if you go back, okay, here, why? Because initially we were only looking at what? At the slices. So we cut the domain into these sub-intervals. Okay? So we are now limited by only working with the building block are these characteristic functions of uh, of you see these characteristic functions here of intervals. So now the question becomes, okay, so this is very, that the approach is very limited. Like for example, and this is one of the fundamental reasons why the uh, Dirichlet function, okay, Dirichlet function, okay, let's call it d of x, which is let's say 1 if x is rational, and 0 if x is irrational. So when you take any interval, if you take any interval for any a and b, a less than b, if you take the characteristic function of the interval ab, okay, then what happened here? Okay, you're going to have a problem with respect to the Dirichlet function, because when you cut, you're going to have that the little m1, the little m, the minimum of this function on this interval will be 0, while the maximum function will be what? 1. So if you go to the lower sum, it's going to give you 0, the upper sums will give you 1, and on any interval, and this will give you what? That the two, there is no way you can get closer, the lower sums and the upper sums, by refining your partition. And that's why this function is not Riemann integrable. And the reason is because we are taking what? We are taking intervals, okay, and the rationals q is dense, okay, in R. So you see, a combination of these two shows you that this function will fail to be Riemann integrable. So this is just a motivation of how do we extend this. So what would be now, what would be the building blocks? What are the atoms that we are going to use? So for that, instead of using the uh, um, the characteristic functions of intervals, we want to use the characteristic functions of subset E. This is what we want now. Okay, so if that's the case, then from there we can define now the s of x, a simple function, to be sigma of mi, the characteristic function of ei's, okay, of x, instead of working what? With intervals. So the question becomes, what is then, how do we do that? How do we make, what would be the integral of this function? So all this boils down, how do you integrate the characteristic function of set E? So the notation that was chosen by many people, starting with uh, Lebesgue, is to call that the measure of E, okay? M of E. Okay, so what are the properties? Sorry about the confusion with this M. This number here is just a number. It has nothing to do. So we want to integrate this S of X. So if we have that, so if you take instead of having M, let us change and put here for the sake of lambda I. So in this case, the integral of S of X dx will be defined as sigma of lambda I by using the properties of linearity of the integral of m of e I. So you see, we can capture this by looking at what would be instead of what is the measure of a set instead of the measure of an interval. Only the building blocks are the intervals. Now we want to extend that to have sets which contains the these intervals. Okay, so clearly for that, so what is the measure of an interval? First of all, okay, this will be b minus a. Okay, so the measure of an interval will be bounded, of course, interval will be I, will be length of I. So why? Because we are trying to fix the Riemann integrals. We don't want to have something totally different from the Riemann integral. So the measure of a set is equal. So this is number one. So what are the properties that we are looking for? Property number number one. So we want, when we translate a set, we want to preserve the measure. Okay? And the one that is very important is that the measure of the union of ENs is equal to sigma of the measure of ENs. So when you have a countable union of disjoint sets, okay, so this is En intersect Em is empty for n different from m. So these are disjoint sets. Sometimes people will not take a countable union. They will only take what? Two sets. The measure of A union B is equal to the measure of A plus the measure of B when A intersect B is empty. So you can have either finite or you can have countably many of them. Okay? So from there we started now to see what's going on. Like for example, it's very simple to see that, okay, the measure of a point, is 0. Okay? This is from, of course, the measure of intervals. We can show this. And then you get from here, you get that the measure of any countable set is equal to 0. In particular, we can talk about what? The measure of Q being equal to 0. Okay? Which tells us now that we can now integrate the characteristic function of Q, yeah, which is, by the way, our Dirichlet function, and find that this is equal to 0. Okay, so it's really interesting. So what are the properties of this Lebesgue integration? So keep in mind, by the way, that this measure will not be extended to all the subset of R. Someone will say, okay, what about now that we have this, maybe any subset, okay, any subset of R bounded, okay, any A subset of R bounded, then we do have a measure of A. Okay? In other words, that any subset will have a measure. And the answer is no. That was given by Vitali. Okay? Who proved that, in fact, if you take any set A in R which is bounded, then you can find inside A a set that that doesn't have a measure, which we call non-measurable set. Okay? So any measurable set A which is bounded, you can find, for example, if you take AB, which we know it is measurable because we are extending the Riemann integration, there exists a set E in it which is not measurable. Okay, does not exist. Okay, so what we are going to do next is play with some problems to go profound in understanding this concept of measures. So keep in mind now, so from here, what do we have now? We are looking at subset A, which belongs to R. So this is the fundamental problem. Sorry, P of R, the power set, or if you want, is a subset of R. And we are associating to it a number, okay, which is in 0 plus infinity, either closed or 0 plus infinity. So we can include also the measure equal to plus infinity. So now, what are the properties of this function m? And keep in mind the motivation that we said just prior to this, okay?